over 2, that n theta, n to the theta, is a reasonable approximation for f of n. Now, to show this, we need to talk. I'm showing this up. That's the limit inferior, and we're using this to compare for accuracy. The limit inferior of fn as compared to n to the theta is 1. But
that's known, you're saying.
It's known. It's proven. Oh, wow. Okay, sorry.
Oh,
The limit
snap.
superior is proven.
Okay.
Is that why you questioned it? You're like, no. No, just not actually. The limit superior equals 1, so that shows that this is a reasonable approximation. But the limit inferior between these two numbers, and this is known as the Stolarski-Haworth constant. And this is a problem that people have been working on for a little bit over 30 years, and an exact solution to this relationship has yet to be found.
By that you mean an exact value of the limit.
Exactly. Now, what? Yes?
Sorry, how did you get theta again?
Oh, theta is just the dimension. It's just log 3 over log 2, because you have 3 self-similar pieces when you take out the middle and you multiply each side by 2.
Okay.
Does that make sense? I kind of explained it the same way. Okay.
Gotcha.
No number for this has been found, and this is Sierpinski mod 2. Now, the interesting thing here is, or Pascal mod 2. Pascal mod 3, they've found an exact approximation for this. And that's what I thought was really interesting. So, this brings into play the question of whether or not this constant, or this number, can actually be found. And that would be very beneficial, because then we would actually be able to accurately track how fractals are changing over time in this particular fractal. Anyways, but they found that for F3n, which is how we're going to denote Pascal mod 3, the limit inferior equals 2 to the log base 3 of 2 minus 1, and the limit superior equals 1, once again. So they were actually also, they're working on trying to find other even numbers, because some people have been able to find exact values for F3n and F5n and F7n. But they haven't been able to find some for any even numbers. Now, I want to introduce one last fractal, keeping in mind that we're trying to find derivatives. And that's Koch's snowflake. Now this is sort of a weird fractal, I think, because the area of it grows as it goes through iterations, whereas Pascal's, or Sierpinski's gasket, stays constant, the area, regardless of how many iterations it goes through. It's always enclosed in that triangle. The snowflake, however, will not exceed, which is pretty easy to see, it's been proven, but it's pretty easy to see, it won't exceed the points of the triangle if you were to connect them into a circle. It will never exceed that now. Does everybody understand how it's... I don't like this picture so much because it leaves the lines there, even though they're green. It would have been better to just remove them. But what it's doing is it's a triangle, and then you're dividing each side into thirds, and you're removing those pieces, and then you're drawing another triangle similar but half the size in each of those places. And you're going to go on infinitely. And you're going to keep just doing that. So I have a question for you guys. If you were to do this an infinite amount of times, what points would be left on the snowflake? Think about it for a minute. You could write it out if you want to.
Sorry, what do you mean by points left on the snowflake? Do you mean like vertices of the triangles? Or
Well, like what would be left of
No, original
the
triangle.
original trees?
The three original.
Oh,
It's just the three vertices.
Just the three. Okay, so what would be left of the second iteration?
The corners.
Just the corners. Okay, so what would be left of the nth iteration?
The corners.
Just the corners. Right. Okay. You guys got it. You guys got it. Okay. So now, as we learned in part 1, you can differentiate this line everywhere but where.
The corner. That's a corner, not a cross.
But if only corners are left, could we actually differentiate this fractal at all? And furthermore, if you can't,
Are they continuous?
then well, are the points continuous? But that's what I was just going to say. Furthermore, if only corners are left and they're all represented by single points, does it matter that they once were corners? Or if they're all basically connected, would they turn into lines? And that's something that people are working on today because they want to see if these fractals are differentiable, and it's not proven either way. So the bottom line is nobody really knows how relevant fractals are in mathematics today. It seems like everything that's being discovered is showing their greater and greater relevances, but fractals right now have the greatest use in physics, specifically fluid dynamics. So if you guys have ever taken that kind of course, you know nobody's taken fluid dynamics. Just wondering. I took it, and we didn't really talk too much about fractals, but they were mentioned. But the first fractal was not actually discovered until 1918 by Julia, and he started Julia Sach.
Julia was a male.
I forgot his last name. Was it Francis Julia?
I honestly
It
don't
was
recall.
Francis Julia, and he discovered the first one. So only since 1918, and he had written this all out by hand. Only since then have we really started to work on fractals, and I think that everything that we're going to discover so far is just going to get really cooler and really more useful as we go on. So I wanted to introduce the idea of differentiability because that's something our group might be talking about a little bit when we go into it. And just to get you guys to think a little, there's not too much exciting, concrete info on fractals. I just want to give you a little taste of what's to come. Question?
Yeah, when you said you can differentiate them, like what are the axes on your graph of that you wrote up there being? Like, what are you differentiating?
They're not going to be axes in the sense of like graphing them on an XY plane. It's more like tracking the rate of change of the ones and zeros over time.
Okay.
And the position of them.
Okay.
So if you could track that, you could see where there's going to be like holes of the zero triangles and where there's going to be like lines of the ones, and those would change over time. Right? You know, if you have a formula for it, then it seems like you would just be able to do it. Do you have any more questions?
Oh, and the guy is Gaston Julia. Francis Julia.
Yeah. Oh, okay.
Gaston.
Yeah, Francis Julia is the English feminist.
Is that from like
Who named?
You know, now you mention that, I think that's
Where
right.
did that name?
Gaston, the
No,
French
I
guy.
didn't
Oh, I
think so.
googled it, so I guess
I-
it's right.
Oh,
It's probably Julia.
Maybe. He's
But I
just
don't
like,
know.
let's call them fractals.
Yeah,
Okay.
because each piece is a fraction of the whole.
It's actually French for snowflake.
Was it Mandelbrot? Was it Mandelbrot who originated the term fractal?
Maybe.
I can
The
Google
term
it.
fractal was coined by Mandelbrot in 1975.
It wasn't
Yeah.
brought.
And it's Mandelbrot for snowflake. Okay.
Oh, that. No, and then fractus, the Latin fractus means broken or fractured. That's it, that's all.
Did you look that up, or did you just?
No, it's right here.
Are there any other questions?
Would you like to suggest a book or article for further reading on fractals for those who might be interested?
Yeah, actually we have one uploaded on the wiki, and it's